We'd like to solve this initial value problem using Laplace transforms. Notice we could solve this with muck. We have the tools to solve it with muck. Soon we will get to problems that we can only solve with Laplace transforms and not with muck. And this is a good kind of transition of practicing some of the easier problems with Laplace transforms before we get to some of the messier ones. So this one will be messy enough as you're about to see. Let's go ahead and start. We take the Laplace transform of the entire differential equation. That gives us s squared capital Y minus s y of 0 minus y prime of 0. That's the Laplace transform of y double prime. That's line 2 in our table. And then the Laplace transform of little y is just big Y. And the Laplace transform of the sine of 2t, that's line 14 in our table. That is 2 over s squared plus 4. So that's line 14 from the table for the Laplace transform of the sine of 2t. What do we need to do? We need to solve this for capital Y. So this is capital Y times s squared plus 1 equals 2 over s squared plus 4 plus, I have 2s plus 1, just 2s plus 1 for now, sorry. So plus 2s plus 1, that is y of 0, this is a 2, and y prime of 0 is a 1. So I put those on the other side, I have 2s plus 1. To solve for capital Y, divide through by s squared minus 1, and now this is 2 over s squared plus 1 times s squared plus 4 plus 2s over s squared plus 1 over s squared plus 1. I could have left that combined as 2s plus 1, but I know I'm going to end up separating it when I do the inverse Laplace transform in a few steps. So I went ahead and separated that fraction already, and I just divided the 2s by s squared plus 1 and the 1 by s squared plus 1 and kept it separate. So we've done the first couple of steps. We've taken the Laplace transform of the entire differential equation, and we solve for y. So those are typically the two easier steps. And then it gets hard where we have to find the inverse Laplace transform of this now. For the inverse Laplace transform, this is right off the table, so that piece is great. I can look at the table and I know what the inverse is. But these others, this one is pretty directly off the table as well. That's not so bad. There's nothing in the table that looks like this, unfortunately, right? This denominator s squared plus 1, s squared plus 4. We don't have that in the table, so we're going to have to do work to get it into the table. And the work that we do is a partial fraction decomposition. This is one of the potential algebraic tricks that you will encounter in almost every Laplace transform problem. You almost always have a partial fraction decomposition or a completing the square or some other algebraic trick along those lines. So we need to do a partial fraction decomposition here. Partial fraction, and that looks like 2 over s squared plus 1 times s squared plus 4 should equal as plus b over s squared plus 1 plus cs plus d over s squared plus 4. These terms are irreducible quadratic factors. What that means is I need an as plus b in my partial fraction decomposition. Instead of just an a, it has to be an as plus b and a cs plus d. That is the most general thing that could combine to give us this common denominator, and so that is what we need. So it's the first part of our partial fraction decomposition. Now we multiply through by the common denominator, and we get 2 equals as plus b times s squared plus 4 plus cs plus d times s squared plus 1. Keep going on this. This is 2 equals as cubed plus bs squared plus 4as plus 4b plus cs cubed plus ds squared plus cs plus d. These get long, and there's bookkeeping. I just foiled these terms together here. And now I need to group the like powers of s. So I'm going to erase, and we'll start over with the like powers of s here and see where we go from there. All right, we gathered all the like powers of s. We combined them, and this is what we have for that. Now we equate powers of s on the left-hand side and the right-hand side. So on the left-hand side, I have an a plus c times s cubed, and I have no s cubed on the right-hand side, so that has to equal 0. Similarly, b plus d times s squared on the left, there's no s squared on the right, so that has to be 0. 4a plus c on the left, there's no s term on the right, so that is 0. And 4b plus d on the left, there is a constant term on the right, so 4b plus d has to equal 2. I now have 4 equations and 4 unknowns, which in general can be really nasty and really messy, but in this case it's not too bad. Let's take these these two, the equations involving a and c, and let me subtract this equation from this one. I'm going to subtract the first equation from the third. That gives me 3a equals 0, which means a equals 0. And if I plug a equals 0 into the first equation, I see that c is also equal to 0. So great news. A and c are both 0. That simplifies things. A couple of our coefficients are 0. Let me do a similar thing with the second and fourth equation. Let me subtract the second from the fourth. So I have 3b equals 2, which means b is 2/3. And that means b plus d is 0, so b must be a negative 2/3. So I have a, b, c, and d, and now go back to our Laplace transform. Capital Y is as plus b, so b is 2/3 over s squared plus 1, plus cs plus d, and d was negative 2/3 over s squared plus 4, plus we had a 2s over s squared plus 1, plus a 1 over s squared plus 1, and this is now ready for me to use the inverse Laplace transforms on the table. I may want to write this as 2/3 times 1 over s squared plus 1 minus 1/3 times 1 over s squared plus 4, sorry, not a 1, a 2, plus 2 times s over s squared plus 1 plus 1 over s squared plus 1. Whew, okay, why did I do that? This now looks like something in the table. And the reason I didn't write this as a 2/3 here, I wrote it as a 1/3 and kept the 2, is because the table requires, when I have the s squared minus 4, if we look at lines 13 and 14 in the table, it's s squared plus a squared and a in the numerator. So that has to match. If I have a 4 down here, I have to have a 2 upstairs. And I can do that. Instead of pulling out the full 2/3, I just pulled out the 1/3 and left the 2 so that I have a 2 to go with that 4. That has to happen in order to be compatible with the table. The table had an a and an a squared. So if there's a 4 here, there's got to be a 2 in the numerator. So this is ready right off the table. This is ready right off the table. All of these are lines 13 and 14 in the table. And I can write the solution of the initial value problem now as 2/3. The inverse of 1 over s squared plus 1 is just the sine of t. So 2/3 times the sine of t. And then I have a minus 1/3. And the inverse of 2 over s squared plus 4 is a sine of 2t. So that is a sine of 2 times t. The s over s squared plus 1, that's actually a cosine. So I have plus 2 times the cosine of t. And then the inverse of 1 over s squared plus 1 is, again, the sine of t. This is the solution. I could combine the sine of t terms and have 5/3 sine of t instead of leaving them separate. That's probably preferable, but that is a big problem, right? We do the Laplace transform. We solve for capital Y. We realize that we're not going to be able to invert without doing partial fractions. So we split it up with partial fractions. We're almost at a place where we can just invert it now off of the table, but we got to get the coefficients right. We got to get the numbers right, and that's how we end up with the 2 to go with the 4. Then the numbers, that's also why I pulled this 2 out and don't have it with the 2s. Then we're ready to just read off the solution off the inverse Laplace transform table, and there it is.